We have assembly. We can write functions, loops, conditionals. But every simple idea requires many instructions. What if we could just say what we want? One line, but what happens underneath? Let's trace exactly how Python runs this. Python doesn't run your code directly. It transforms it through several stages. Source code to tokens, tokens to an abstract syntax tree or AST, tree to bytecode, bytecode to the interpreter. Each stage brings us closer to the hardware. Let's trace a simple loop for every stage. Watch what happens to this program. First, Python breaks your code into tokens. Keywords, names, operators, numbers, the raw pieces. Then Python builds an abstract syntax tree. The AST captures the structure of what you wrote. A tree of operations, not just a sequence of characters. The for node has a target, the variable I. An iterator, the call to range with argument 3. And a body, an assignment using a binary operation. This is where Python understands your intent. From the AST, Python generates bytecode. Let's see the actual bytecode for our loop. Each instruction is a single operation with its arguments. Load name gets range from memory. Call invokes it with argument 3. GetIter creates an iterator. For iter gets the next value or jumps to N4 when done. Binary op performs the addition. And then jump backward. It jumps back to the for iterator. This is the loop. A simple for loop broken into primitive steps. Who runs this bytecode? The Python interpreter. Written in C, let's peek inside. A giant switch statement, one case per bytecode instruction. Load name looks up a variable and pushes it onto the stack. Binary op pops 2 values, adds them, pushes the result. Jump backward subtracts from the instruction pointer. This C code compiles to assembly. There it is, J and Z, jump if not 0. The same instruction we built in episode 6 for flow control. Let's see the full journey. Python to tokens. Tokens to AST. AST to bytecode. Bytecode to the C interpreter. The C interpreter to assembly code. Assembly code to machine code. Machine code to the CPU. The CPU uses the ALU, which uses the adder, which uses XOR and AND gates, which are all built from NAND. One Python line, 10 layers of translation, all the way to NAND. This is what abstraction looks like, and now you can see through it. All these layers have a cost, though. Each translation takes time. Python is slower than C. C is slower than assembly. But for most programs, developer time matters more than CPU time. For AI, we need both expressiveness and speed. Python controls the logic. Optimized libraries do the math. NumPy, PyTorch, they're written in fast C and Fortran underneath. Best of both worlds. From NAND to Python, each layer hides complexity and reveals power. Python will be our tool for the rest of this journey toward GPT. Next time, what happens between import torch and the GPU?